All right, this is the second lecture in chapter 4. We're talking about probabilities, and last class we discussed some basic introductory concepts to the probabilities. And I hope we can finish this chapter today. We'll try. At the end of last class, I think I told you about the marginal probabilities. Okay? Right now, what you see on the margins here, we can calculate the marginal probability based on those numbers. For example, marginal probability is a probability of a simple event. Okay? So since we have total of 4 aces in the entire deck of cards, right? The probability for ace would be 4 divided by 52, which is the total. Okay? All right. And that's how we calculate the marginal probability. Probability of picking a red card, for example, would be 26 out of 52. Okay? All right. And then today we need to start out with the general addition rule. It's a pretty simple concept, I think. Most of you have used this concept already. I think you have pretty good ideas on the addition rule. Okay? But let me quickly illustrate this idea. Suppose we have 2 events, A and B. Okay? And the probability that we will have A or B, notice that it is or. Okay? So in symbols, we frequently write it this way, and we read it as union. A union B in a set theory. Okay? This is called the A union B or A or B. Okay? So if you have 2 possible events, let's say A is an event that you will pick an ace, B is an event that you will pick a black card. Okay? Then if you pick 1 card out of the total 52 cards, okay? What is the probability that you will either pick an ace or black card? Okay? That's the idea of this idea, the B, A union B. Okay? All right. That probability would be probability of A plus probability of B minus probability of A. What do we call this? This is A intersection B, right? And this is also, we call it joint probability. Okay? This is the probability that event A and event B will occur jointly at the same time. Okay? So graphically, we're talking about this area, this overlapping area. Okay? This is A intersection B. Okay? So, logically you can understand what we are doing here. We're trying to find out the total area covered by A and B. So if you pick any element at random out of entire sample space, we're trying to find out the probability that element will be somewhere in this area. Okay? So if you add probability A, this size, to the probability of B, which is this size, then we are adding this particular area twice. Okay? So that's why we are subtracting that area once. Okay? That's the idea. That's what we call general addition rule in probability. So probability A or B or A union B is equal to PA plus PB minus P intersection joint probability between A and B. Okay? Well, we can think about one special case. Okay? In case A and B are mutually exclusive, I hope you still remember the concept of mutually exclusiveness. Okay? There is no overlapping part. Okay? So in case we have two events like this, A and B, right? There is no overlapping part. In other words, there is absolutely no chance, no probability that both events will occur at the same time. Okay? So in that case, well, then obviously this is 0 because there is no overlapping portion. Okay? So that the union A or B simply becomes PA plus PB, okay? Or mutually exclusive events. Okay? Okay. Now, based on the concepts of marginal probability and the addition rule, now we can talk about the conditional probability. This is a very interesting and useful concept. Okay? Conditional probability is the probability of one event given that another event has occurred. Okay? And we write it as A vertical bar B, and we read it as A given B. Okay? The meaning of that is, well, this is the conditional probability of A given that B has already occurred. Okay? And the way we calculate it, we can calculate it by dividing the, what is this? Probability A and B. What kind of probability is that? Joint probability. Very good, right? Okay. So we divide the joint probability by probability of B, a simple event. What we call probability of a simple event. Probability of simple event like this has a special name I just mentioned a few minutes ago. Marginal probability, yes. Okay? So conditional probability is simply joint probability divided by marginal probability. Okay? And make notes that this B, the event after the vertical bar, okay, that is the condition. That is the event that occurs already, first. Okay? So you can think about probability of A given B, or you can think about the other way around. Okay? This is the opposite case. Probability of B occurring given that A has occurred already. Okay? Well, in that case, it will be joint probability divided by marginal probability of A. Okay? Well, what's the use of this conditional probability? Let's say, well, let's use an example. Okay? Suppose you are trying to buy a car. And being a poor college student, you can't afford a new car. So you went to a used car lot. Okay? And there are so many cars on this used car place. Okay? Let's say 100. Okay? They have 100 used cars. Okay? And some cars have CDs, CD players. Okay? Some cars don't. Okay? And of course, for college students, CD player is pretty important. Is it? Is it still important? Not really, right? Everybody uses thumb drive or smartphone, right? Well, apparently this example is a few years old. Okay? And some cars have AC, air conditioning, and some cars don't. It's hard to imagine that, there's any car not having air conditioning these days. Okay? But, if you go to some parts let's say, in the United States, for example, I spent about 9 years, I lived 9 years in Cleveland, Ohio, okay? Which is right under the Great Lakes, Lake Erie. Okay? And I would say about 9 months of the 9 months of the year is winter. Okay? That's pretty cold area. Okay? The summer weather in Cleveland is perfect. July and August, that's the wonderful season in Cleveland. Okay? You don't really need any AC in that area in your car. Okay? You definitely need a good heater. Okay? My second daughter's birthday is June 26th. Okay? And when she was about maybe 6 or 7 years old, we invited some friends to have a birthday party. Okay? We were having a party in the backyard. Okay? And suddenly it started to snow. Okay? Late June 26th, it snowed. Okay? Matter of fact, in Cleveland, if you look at the history, the statistics, okay, they had snow in every month of the year. In other words, they had snow in August, even in August. Okay? So, think about those areas like Minnesota or Upper Michigan. Upper Michigan is another wonderful place to be in the summertime. Not a very nice place to be in the wintertime. Okay? So let's say some of the cars didn't have AC. Some cars had AC. Okay? So if you look at this contingency table, you can figure out, let's say, if these are probabilities. Okay? Probability of AC is 0.7. Probability of no AC is 0.3. Probability of CD is 0.4. No CD is 0.6. Okay? So if you had 100 cars in the lot, right? How many cars would have AC? 70 cars, right, apparently. 70 cars, 70 out of 100 would have AC, and 30 out of 100 do not have AC, right? So these are what probabilities? Marginal probabilities, right? Marginal probability of AC, marginal probability of no AC, and so on, right? What about these probabilities inside? 0.2, what are we talking about here? Joint probability between CD and AC, right? So that's the probability that if you picked one car at random out of entire 100 cars, right? That's the probability that you will have what? You will find a car with both AC and CD, right? And that's only 20 out of 100, right? 0.2 out of 1.0, right? So only 20 out of 100 cars have both CD and AC, right? How about this? Can you describe this probability? What is it? That's right? This is the car with AC but no CD. In other words, that's the joint probability between these two events. Okay? And so on, right? So all these probabilities inside the table are joint probabilities. Okay? The outside, on the margins, are marginal probabilities. Remember that, okay? So you can ask a question. Somebody spilled something here. What is the probability that a car has a CD player given that it has AC, right? So if they collected all the cars with AC on one side of their lot, right? Then out of those cars, so once you forget about all those cars without AC, right? Now we are talking about only those cars with AC, right? Then what's the probability that you will find the car with CD, right? That's a conditional probability, right? Probability of finding a CD given that AC has occurred, event AC has occurred, right? Well, according to the rule, or formula, conditional probability is joint probability divided by marginal probability. Again, marginal probability is for the condition, right? All right, so according to this table, joint probability is 0.2. Marginal probability of AC is 0.7, right? So 0.2 divided by 0.7 you can calculate it 0.2857. Okay? That's the idea of conditional probability. Okay? There's another way to illustrate this example. Okay? It's called the decision tree diagram. Okay? I think I briefly explained this before, but we have branches. The point from where the branches stem out or emanate, right, are called nodes. Okay? So we have starting the first node. From there, we separate between AC and no AC. And among the ACs, we have another branch or node, okay? Separation between CD and no CD, and among all the cars that do not have AC, CD, and no CD. Okay? So we can write it this way, 0.7, 0.3, those are marginal probabilities. Okay? And then the conditional probabilities, yeah, as we've seen there, right? If you multiply this to this, what do you get? Right. So from there, we find another useful fact, okay? From the fact that conditional probability is joint probability divided by marginal probability. Okay? We can say joint probability is, let's say, marginal probability times conditional probability, right? Okay. So this decision tree diagram illustrates that fact, right? This joint probability is simply marginal probability times conditional probability. Okay? All right? Are we following so far? Nothing difficult, right? Nothing complicated. The next slide is another decision tree diagram. This time, instead of starting out from AC, we started out with CD and no CD, right? So we have different conditions. This time we started with finding all the cars with CD, and among those cars with CD, we try to find the probability that we find a car with AC or no AC, and so on. Okay? The same idea. Okay? All right, so at this point, we are ready to talk about multiplication rule. We just talked about addition rule, general addition rule a few minutes ago, right? Here's another rule. Okay? Multiplication rule says the joint probability between A and B is the conditional probability A given B times the marginal probability of the condition, right? Which is exactly what we have here, right? Joint probability is the conditional probability times marginal probability, okay? All right? And we've seen the example, we've seen the idea from this probability tree diagram, decision tree diagram, okay? If there is a special condition, it's called independence. Okay? Here's another concept, new concept in this chapter, independence. Okay? If A and B are independent, what that means is the probability of one event is not affected by the fact that the other event has occurred. Okay? So two events, A and B, are independent. That means whether B has occurred or not does not change the probability of A. Right? Or whether A has occurred or not does not affect probability of B. Okay? So two events are completely separate or independent. This requires a little bit of explanation, right? Try to think about two independent events. As you know, right now, they are trying very hard to find any debris from flight MH370, right? Malaysian airline, right? Just simply disappeared, right? And it's very sad thing for all the families, right? They don't even know whether they are still alive or, well, I'm sure the family members are still hoping that the passengers are still alive, right? Somehow, miraculously, right? And I don't think they'll give up until they find, concrete evidence. Okay? Anyway, so people ask the question, if you fly often, if you're a business person, especially when you're young, right? You get a lot of assignments, a lot of travel assignments, right? Some people I know travel every week. They go all over the United States or sometimes other countries every week, right? So if you fly every week, is there the likelihood of you getting into a crash, right? Is that pretty high? Does it increase your likelihood of getting involved in an accident, airplane crash? Right? Yes? No? Why not? Okay. Why? Why does it stay the same, even when you fly every day or every week? Mm-hmm. Okay, that's fine. Okay. Yeah. Okay. Okay. Right. Well, yeah. The point is, you can fly frequently, but every time you get on the get on the airplane, the probability of getting into a crash is constant, right? And each flight is independent, right? So, if there was a big crash last week, right? Does that mean this week the airplanes are more likely to crash or less likely to crash, right? So every flight is independent, right? So people who fly often always believe that, right? But the thing is, you are subjecting yourself to the probability more often than other people, right? So I would say, yeah, it is, of course. If you compare the probability of getting into crash between two people, one people fly every day, one people never fly, right? Then, of course, people who fly more frequently is more likely to get into an accident. Yeah? But, that's the idea of independence. Yeah? Each trial is independent. If you flip the coin twice, okay, whether you got head or tail in the first flip, does that affect the second attempt, second trial, right? So when you flip the coin, each trial is separate, or each trial is independent, right? In other words, whether you have had head or tail does not affect the probability of head or tail in the second trial, right? That's the idea of independence. Okay? If two events are independent, if A and B are independent, then conditional probability of A given B should be equal to probability of A. In other words, the probability of B, the probability of the conditional event, does not make any difference in the probability of A. Okay? Let me use another example. Okay. Let's say gender and the student loan default rate. Right? Gender and student loan default rate. Most college students obtain loans to pay for tuition. Okay? And I guess it's also a problem or concern in Korea as well. But in the United States, these days, the average college tuition is so expensive, right? A lot of students, in fact, most students graduate with a lot of debt on their shoulder, right? So, after 6 months after graduation, they are supposed to start paying off their loan, okay, unless there is some circumstances. Okay? But some people obviously cannot make the payment, okay, and default. Default means, they miss the payment, right, many times, right? All right. So let's say you collected some data, okay, and here default, not in default, okay, and you categorize them between male and female, okay, and suppose we got 18, 42, 12, 28, okay, so that's 60, 40, and 30, 70, and total of 100. Okay? So you collected the data from 100 graduates, college graduates, okay, and categorize them between male and female categories and default not in default category. Okay? And we got this result. Okay? Then let's think about the probability of default given that the graduate was male. Can you calculate it quickly? If you picked one student at random, one student among the males, right? So given that the graduate was a male, what is the probability that the person is in default? 3 out of 10. How did you calculate it? Conditional probability is joint probability divided by marginal probability, right? So joint probability between male and default is here, 18, right? So 18 out of, the condition male is 60, right? Of course, in order to be probability, you have to do 100 divided by 100, 18 divided by 100, or divided by 60 over 100, right? But, so that's 0.3, right? Well, what about probability of default? What's the marginal probability of default anyway? That's 30 out of 100, right? 30 out of 100, which is 0.3, right? So here we find, right? The probability of D, or in default, given that the person was male, is 0.3. But probability of being in default anyway, whether you are a male or female, right, is also 0.3, right? So what that means is whether the condition is satisfied or not. In other words, whether the person was male or female, right, didn't make any difference, right, in the probability of being default, right? That's the idea of independence. Okay? Okay? Make sure you're able to verify independent. Okay? Well, if that condition is satisfied, if A and B were independent, then we know this, right? So we can substitute PA for this conditional probability, which means the joint probability between A and B will be simply PA times PB. PA times PB. If A and B are independent, right, then joint probability will be simply just multiplication between A and B. Okay? All right? Does it work here? Make sure you check it out here. So joint probability of being a male and in default, right, which is 18 out of 100, should be this marginal probability of M, which is 0.6, times probability of default, 0.3, right? That works, right? What about other cells here? Why don't you quickly check, right? So in terms of probabilities, this is 0.3, 0.7, 1, 0.4, 0.6, right? So 0.818, 0.42, 0.12, 0.28, right? So joint probability here is 0.6 times 0.7, right? It checks out, right? How about here? 0.28 is 0.4 times 0.7. Okay? Right. So if two events are independent, it becomes very simple. Okay? Now, so before we go on, let me, in decision tree diagram, okay? Okay, so let's say starting out with the male of, using the same contingency table, suppose we try to illustrate it with the decision tree, right? So probability of male is 0.6, probability of female is 0.4. All right? And then, you know the conditional probability, okay? Here, there should be probability of being in default given male, right? But we've just found out that those two events are independent, right? So we can simply say it is PD, okay? And this is P D prime, not in default, okay? And this is probability of D. Again, originally this was D given female, right? Out of female, what's the probability for being in default, right? But now we find out that they are independent, just like here, right? 0.12 is okay, right? Okay, so probability of, okay. So joint probability, we find out probability of M joint D, probability of M joint D prime, probability of female joint D, probability of female D prime, right? These are simply 0.6 times 0.3, which is 0.18, right? 0.42, 0.12, 0.28, right? So in a decision tree, the point I'm trying to make here is this. In a decision tree, we have one event and the second event, right? If the two events are independent, then we can simply multiply this probability times this probability will give us that joint probability. Okay? if two events are independent, right? So you can apply this idea in many different situations. Simplest case will be you're flipping a coin twice, okay? So first attempt, second attempt, third attempt, you can go as many attempts as you can. Well, that's a little bit too obvious because coin is, I guess we mean fair coin. So it's half for all the way, right? 0.5 for head, 0.5 for tail, right? So let's say first event is flipping a coin, second event is rolling a dice, right? Then we're going to have a lot of branches here, right? So head, tail, given that you had the head, second event is you roll a dice, right? So there are 6 possibilities. And from each node you have 6 possibilities, right? And so on, right? But if two events are independent, you can simply multiply, right? So let me ask you quickly, right? If you had that experiment, in the first attempt, first trial was flipping a coin, right? And the second trial was rolling a dice, right? What is the probability that you get a head in the first trial and number 3 in the second trial? What's the probability that you will have head and number 3 in this in this experiment? 0.5 times 1/6, right? Because we're talking about probability of head is 0.5, probability of tail is 0.5, right? And here each possibility is 1/6, 1/6, 1/6, right? Right? So probability that you will get a head and number 3 is simply 0.5 times 1/6, right? Because we can reasonably assume that these two events are independent, right? Whether you got a head or tail in the first attempt does not affect the probability in the second attempt, right? Okay? So that's the idea, right, of independence. Independence and the decision tree diagram, right? Well, if you go back to, this tree diagram, right? And go back to this table, you can do it on your own at your leisure time, right? Whether this example works the same way as this example. In other words, are these two events, CD and AC, independent? Make sure you try that, right? Then you will find out they are not. The probability that you will find a CD in a car is not independent from the probability of, the event that you find a CD in a car is not independent from the event that you find an AC in the car, right? Then you cannot simply multiply like this, right? You cannot simply multiply this one and find the joint probability, right? So what I'm talking about here, in other words, is this. If two events in this tree diagram, this event and this event were independent, right? Then the joint probability would be simply marginal probability times marginal probability, like this, right? Marginal probability of head times marginal probability of 1 or 6 or 3 or whatever, right? Any number, right? So joint probability will be simply marginal probability times marginal probability, right? But in this case, because they are not independent, two events are not independent, you have to do marginal probability times, what are these? Conditional probability, right? So this always works. joint probability is marginal probability times marginal probability. This will be true if what? Two events are independent, okay? But joint probability equals marginal probability. Sorry about my writing, but I'm sure you understand, right? Marginal probability times conditional probability. This is always true, right? That rule is always true, right? Make sure you remember that. Okay. Question so far? Are we doing all right? Okay. So now we are ready to move into our final topic. But here, okay, before we talk about Bayes' theorem, where's the, okay, here we go. Let's try to understand this. Marginal probability for event A, we can rewrite it as this way. If we had certain events, B1 through Bk, that are mutually exclusive and collectively exhaustive. You remember those concepts, right? Mutually exclusive. Mutually exclusive and collectively exhaustive, right? So, last class he illustrated very well, right? If you have, say, B1, B2, B3, okay? Then these three events are mutually exclusive because there is no overlapping portion, right? And collectively exhaustive because these three events cover entire sample space, right? There is no uncovered space, okay? There is no other possibility other than B1, B2, B3, okay? And then we're talking about another event here, A, okay? A. Okay. Then the total probability of A is conditional probability A given B1 times PB1, right? But remember, this is conditional probability times marginal probability. What is it? That's joint probability. So you can rewrite it as this whole rule, right? Can be rewritten as BA is PA joint B1 plus probability of A joint B2 plus up to whatever probability of A joint BK, right? The only requirement here is B1, B2 up to Bk. These are mutually exclusive and collectively exhaustive, right? You have to satisfy that condition like this, right? Right? And if you think about this illustration diagram, it's a very obvious statement, right? Because what's the intersection between A and B1? A and B1 is right here. That's the intersection between A and B1, right? How about intersection between A and B2, right? That's right here. Okay? And finally, we have only 3 possibilities here, B1 through K, 3, right? So the intersection between A and B3 is right here, right? So if you add them up, what do you get? That's total probability for A, okay? So it looks complicated, but it's a simple idea, right? Simple concept, right? But we need it for Bayes' theorem, which is our final destination in this chapter, right? Bayes' theorem, right? Everything we talked about so far was in order to lay the foundation for this Bayes' theorem, okay? Which is a very simple idea. You don't have to be scared, okay? The idea of Bayes' theorem is to revise previously calculated probabilities based on new information. So we have certain probabilities already, right? But we have some additional information. We got a new fact or new data today, right? And based on this new information, we are trying to revise previously known probability. It's called the prior probability, okay? And, well, don't worry about it if you don't understand it. We're going to use an example, then you will understand it. Okay? Introduced by Reverend Thomas Bayes, okay? Who was an English clergyman, okay? Presbyterian minister. Okay? You know, in the 18th century, the priests, Catholic priests, and the Protestant ministers were people with the most education. Okay? Not only in theology, but they all had, most of them had some interest in other fields like biology or mathematics or economics. Okay? And a lot of these clergies, okay, or people, the ministers and priests, made contribution to many different fields. Okay? I told you about the Cleveland. I was an assistant professor in Cleveland, okay? And it was a Catholic school. Okay? And it's called the Jesuit school. Okay? So they have a lot of professors who are actually priests, Catholic priests. Okay? And their title goes Father, say, James, whatever, Hubbard, S.J. Okay? S.J. means the Society of Jesus, okay? Which is Jesuit. Jesuit is just a denomination in Catholic. Okay? But this denomination emphasizes education so much. Okay? So they train their priests in many different fields. Okay? So a lot of their priests have PhDs in, astronomy or mathematics or sociology or, and that's a very good way to save money actually, okay? Because a lot of professors in the university are priests, okay? And I don't think they pay a lot of money to priests, okay, for teaching. Okay? Anyway, so it is introduced by Thomas Bayes, Reverend Thomas Bayes. It is an extension of conditional probability. So based on the conditional probability that you learned so far, you should be able to understand the Bayes' theorem. Okay? And here's the actual theorem. Probability of BI. We talked about this B1, B2, BK, right? So probability that any of those events will occur, given that another event has occurred, can be calculated with this formula, okay? And looks complicated, but think about the denominator at the bottom here. What is it? We just saw that, right? In the previous slide. Yes, that's simply marginal probability, right? A given B1 times B1, right? Conditional probability times marginal probability, right? So if you add them up, that's exactly probability of A, right? What about the numerator on top? What can you say? That's conditional probability times joint probability, right? So actually, that's one of all these items. One of all these terms, right? So that's another joint probability, right? So joint probability divided by marginal probability, right? That's Bayes' theorem. Well, you don't have to worry about, you don't have to remember, because of course, when you take an exam, you can use cheat sheets in my class, right? But there's an easier way. Here's an example. Example helps a lot to understand. Why don't you read and try to understand what the story is? Drilling company. So let's say you're trying to invest in oil well, okay? And oil exploration is a risky business. It's a gamble. You spend a lot of money to drill a certain site, right? Of course, before you start drilling, you will do all kinds of tests. Okay? And if there is any chance of finding an oil, you will start drilling, right? And sometimes you hit, sometimes you don't. Okay? It's called the gusher. Or dry well. Okay? Gusher means you hit the jackpot, right? You get a lot of oil from that well, right? Have you seen the movie Giant? James Dean movie? You should watch it. It's a great movie, right? And there's one impressive scene. James Dean tries to find the oil, and he was a lot of pressure from other people to sell his tiny patch of land. But he doesn't relent. He doesn't give up, and finally hits the oil, and suddenly the oil spews out, and that black crude oil spreads out, and James Dean is completely covered with this black oil, but he just laughs and cries and enjoys. Okay? It's a wonderful scene. James Dean. You know who James Dean is, right? Okay, good. So I really recommend you to watch that movie Giant. Okay? Anyway, so here, historically, they know that 60% of successful wells have had the detailed test. All right? So you should have certain prior knowledge, and that is like this. Okay? We have two events. We have two events: successful well, unsuccessful well. Well, actually, yeah, I guess you can say it's a one event, whether it's a successful or unsuccessful. Suppose probability of success is 0.4, unsuccess or failure is 0.6. Okay? That's what we call prior probabilities. And then we can use another event or another information, right? And this, let's say that event is D, or detailed test as D. Okay? And given that the whale was successful, so based on the past history, past data, we know that among the whales that were found to be successful, right, the 60% of those successful whales tested positive. Okay? And among the whales that were unsuccessful, only 20% of those whales tested positive. Okay? So make sure you understand the structure of this setup. Okay? We start out with a prior probability of success in an event, right? And then we were given another information, okay, about this conditional probability, right? And based on that, we're trying to find, it's called the revised probability. It's reversed, okay? I mean, reversed, but we're talking about revised probability. Okay? So based on the new information, we're trying to revise the prior probability and come up with the revised probability. Okay? So once we know the test is positive, what is the probability that we will find a successful whale? Okay? Well, you can use the formula like this. This is the application of this formula, right? Because you have all this information, you can plug in the numbers, okay, and find the revised probability. But I would recommend this tabular approach. This is a lot easier, and it eliminates the possibility of, or reduces possibility of committing an error if you use this tabular approach. Okay? So first you list two different possibilities, or sometimes it's multiple possibilities, right? If you can have many different possibilities. It could be very successful, be moderately successful, and not successful, or completely dry hole, or something like that, right? You can have many different possibilities, right? But here we have simple events of success and not success, right? And then we have prior probability, 0.4 and 0.6. So we know that based on the prior history. And then we were given this conditional probability, right? So all right. You can write it this way. SI, or event I. So you write down the event success, the unsuccess, okay? Probability of SI, that's prior, it's right here, the prior probability, okay? So that's probability of SI, okay? And then the next one, conditional probability, is condition being satisfied given that the first event was S or S bar, okay? So this is probability of the test being positive given that it was success, and probability of D given that it was a failure, okay? And then the next column would be joint probability, probability SI joint D, right? And joint probability, as you know, is simply the marginal probability times conditional probability. Okay? Remember, this condition is SI, and these are the probability for SI. Okay? So you can just simply multiply, right? And then you have to do one more thing here. Here you have to add them up, summation of all this, okay? And that would be marginal probability. Okay? We're talking about this idea. Okay? You know, these are all joint probabilities. Okay? So when you add up joint probabilities, you come up with the marginal probability. Okay? Okay? So you add this and this, you come up with the marginal probability here, 0.24, 0.12. So marginal probability of 0.36. Okay? All right. Then finally, we come up with the probability of SI given D. Remember, that's the reversed case, the opposite case. We call it revised probability. Okay? So, story is this. Here, we're trying to find assess the probability of success in any oil well exploration. Okay? And based on the previous history, we have this prior probability. On average, 40% of the wells are successful, 60% of wells are unsuccessful, right? But then we can do a little more than that. There is what's called the detailed test, maybe geological test or something, right? And we also have that information. Given that the well was successful, the probability that the test will produce positive result was 60%. Given that, or among the holes that are unsuccessful, right, probability that the test will come out positive was only 20%, right? So using the conditional probability, we calculate the joint probability of two events, right? Successful and test positive, unsuccessful and test positive, okay? And we come up with these two joint probabilities. So when we add them up, we come up with the marginal probability, okay? Marginal probability, where did I leave? Okay. This is probability of D, you can say. Okay? Probability of being test positive. Okay? So out of that 36 or 0.36 possibility of being tested positive, okay, what is the chance? Right? So here, given that the test came out to be positive, what is the probability of success? Right? That is simply joint probability divided by marginal probability. Joint probability divided by marginal probability, so 0.667. Right? So we have revised our prior probability, 0.4, given with the given information about another test. Okay? And the revised probability is 0.667. So I guess the test helps in this case. You know, we're trying to invest millions of, maybe hundreds of millions of dollars. Okay? Without this additional information, we had very crude information, the simple probability of success and not success, right? But then, can we use another information to refine, so to speak, right? Refine that prior probability, right? So using the test information, we have come up with this information, which means if the test produced positive result, right, then the probability of finding oil or having a lot of oil is almost 70%, right, instead of 40%. Okay? All right, so that's an example. Any question? Okay, I'll see you Tuesday.